Of Nati.
Okay. Okay. Thanks. So, just to recap what we talked about yesterday. So we're talking still about the convex setting. And we talked about. We said that learning really is optimization. Learning is just solving a stochastic optimization problem. So we're talking about optimization problems of this form. We want to minimize some stochastic objective and expectation over z, and we want to do it based on samples of z, or really we're going to use the z's just to get unbiased estimates of the gradient. And we'll write things generally for general objective f, but really what we should have in mind for learning is an objective of this form, a loss for a linear predictor. And as we said, when we talk about convex learning, we want the objective to be convex. We kind of have to talk. We're really limiting ourselves only to linear prediction. One thing also, so it's a question that Lenka asked last time after the lecture. I want to just explain why this is very generic. So in some sense, any predictor can be written as a linear predictor over a rich enough feature space. And we'll see that the way we're going to in fact treat this in this later half of this talk and next time is we're going to view this what we're calling here W, the linear predictor, is really just specifying all functions, because really this W has to live in some vector space. The space of all functions is also a vector space, infinite dimensional vector space. So if you want to think of it that way, think of phi as just mapping x to an indicator, right? In the think of a discrete space, and then you can represent any function as a linear function over x, right? So if x, if x has cardinality 1,000,000, just map it into a 1,000,000-dimensional space where each element just gets mapped to an indicator, right? And then any function over x you can write as a linear function with that representation. Okay? So this is very generic, but we are here in some sense talking about linear prediction. And the kind of crux of the reason, we said there were two reasons for talking yesterday about convex optimization, because what are we? This is a deep learning school. Why are we talking about convex optimization? And so we said there are two reasons. One reason is to present a mirror descent algorithm, which we'll get to, and the other is to see how in convex optimization we have this understanding of the relationship between inductive bias, or the complexity measure we bring in, and the geometry. And that comes in, and we'll see it very clearly in mirror descent. Through mirror descent, where mirror descent is an optimization algorithm with a local geometry, and we'll try to understand this also intuitively today, that's directly tied to a complexity measure. So we have this complexity measure psi, okay? And in some sense, where mirror descent, so we know that if this complexity measure is the Euclidean norm, or the squared Euclidean norm formally, so it'll be strongly convex, then that kind of corresponds to gradient descent. If we're exploring the space with gradient descent, we're implicitly kind of looking for solutions that, the generalization is going to be linked to the L2 norm, to the Euclidean norm. We're kind of implicitly constraining stuff with L2 norm. What happens if we want to use a different complexity measure? If we can represent it as some psi, which is at least for now strongly convex with respect to some norm, then we can use mirror descent. Okay, so let's try to understand mirror descent. And formally, we wrote mirror descent as so we actually derived it in terms of regularizing this objective based on the first order approximations. But we saw that this amounts to writing updates of this form, where at each step we minimize the linearization about the last iterate and using just one sample, so a stochastic linear approximation to our function. And of course, we don't want to just minimize the stochastic linear approximation. First of all, it's stochastic, so we don't want to pay too much attention to it. And it's only the linear approximation is only value close to WK, so we don't want to go very far. And so we minimize it plus some proximity term. Then instead of looking at the squared Euclidean distance like in gradient descent, we look at the Bergman divergence corresponding to psi. And this, as we saw last time, turns out the right thing to do. And we said we can understand it in various ways. We talked about two ways last time. One is with this proximity operator, or even two. One is with this proximity operator. Another is by thinking of psi. This corresponds to, we said, think of psi as the regularizer. And another, which gives mirror descent the name of mirror descent, is jumping between the primal space and the dual space. So the primal space is a space of W, and again, you can think of it as column vectors, and the gradients are row vectors. They're linear operators on columns. They live in the dual space. So I can directly add the gradient. And so what we do at each step is we take our current iterate WK, we map it using a link function given by the gradient of the potential to the primal space. Now we're in the primal space. Here we can add the gradient. Okay, so the gradient actually lives in this. In the dual space, we add the gradient, and now we map it back to the primal space using the inverse link function. Okay, so a potential function also defines a correspondence between points in the primal and dual space. And the way we presented it last time. We also said what happens if you want to constrain ourselves to a set, some convex subset of this vector space. And for the rest of today, we're going to ignore this constraint, and so I'm going to remove the constraint here and remove the projection over here. I should say that. I'm sorry. What question? Okay. And I should say that this is done partially for simplicity and partially because we actually, some things we don't exactly know. I mean, they become more complicated in ways. So some of the things are just to save time, and some of the things is because I don't actually fully understand what happens when you have the constraints. And you can ask me maybe later what happens if we do have these constraints. Okay. Okay. So what we want to understand now is also try to understand mirror descent in another way. And in order to do that, so another change I want to do here on the board before we continue. We wrote here lambda k as a kind of, we think of it as a regularization term, is regularizing each iteration. But what we said is both in gradient descent and mirror descent, this basically translates to a step size, right? To how much, the more I regularize, the smaller steps I take, okay? So I'm going to rename this lambda k is 1 over step size, 1 over eta k. And that's the notation we're going to use today. Okay. So what we're going to try to understand is understand how this looks like. In particular, when the step size is small, then let's, what we're going to do is just take a low order approximation of the Bregman divergence. Okay, so we said if we're looking at the Bregman divergence between W and WK, and we'll take an approximation where when W is close to WK, right? Where the next iterate is going to be close to WK. Okay. So let's do that. So we're looking at this. We're taking approximation with respect to W. So we give the gradient of psi. So starting from here, we'll take a second order approximation. So we have the gradient of WK times W minus WK, the first order term. And then as we'll see, this is going to cancel out. So we're going to include also the second order term, which is going to be the significant term here. And the second order term is W minus WK times the Hessian of the potential function. And then this term, I'm not going to bother with it. I mean, this is just going to be, this term doesn't depend on W, or since what we're going to be concerned with is minimizing with respect to W. I don't care about terms that don't depend on W. I mean, they're not going to affect my minimization problem here. Okay? And then the other term here that actually depends on W is the, why is this upside down? I'm sorry. Is the gradient of its W prime times W, and that we're just going to leave as is. That my sign is wrong. Oh, I have parentheses here. Good. Minus gradient of wk times wk. Okay, so this term, times w. So this term doesn't depend on w. We can ignore it. And the first order terms here cancel out. Okay, and what we're left with is just this Hessian term. Okay, and so this means we can approximate the gradient descent step as just using a quadratic proximal term, which is w minus wk times this Hessian times w minus wk. Okay. So what we got is something actually locally similar to gradient descent, but it's not exactly gradient descent. It's gradient descent with respect to some other quadratic norm. So it's some kind of conditioning that depends on where we are. Okay. So this is just quadratic, like gradient descent. We can solve it, and what we get is that wk plus 1 is just solving this quadratic wk minus eta k times the inverse Hessian times the gradient. Okay, so let's try to understand what's going on here. So again, we started from some complexity measure or regularizer psi, and what we're getting here is that infinitesimally the way the dynamics look like is that we're taking each time a step kind of conditioned on a step conditioned on this inverse Hessian. The way you can think about it is that we have a local metric here. So each step, what we're trying to do with the gradient descent, each time we're trying to taking a step that improves the objective as much as possible, or at least the stochastic linearization of the objective, and is small in some kind of metric. Okay? And we can see that we can think of this metric as some kind of local quadratic metric. Okay, so this is really what when I think about like changing the geometry of optimization algorithm. Okay, it tells you at each point in the space kind of which directions are cheaper, which directions are expensive, which directions do you like to go, or which directions do you not like to go. Right? Directions where this Hessians are very, very large are directions you don't want to go, right? Because going in that direction actually corresponds to a large distance in your local metric. You should think of this as a local metric. Okay? If the directions in which the Hessian are small, okay, you don't mind going there, that actually you consider that cheap. Okay? And so this is maybe the best way to think about it. And so in particular, we can think of this as defining some metric tensor rho of wk. Okay, so this is without the inverse. So the Hessian of the potential is just rho of wk. Okay, okay. And once we write it, okay. So now this approximation to mirror descent also actually has a name on its own. So this is exactly the optimization algorithm known as natural gradient descent. Right? So this is mostly popularized in the context of information geometry by Amari, but again, it's valid for any potential psi, or really for any metric tensor. So another way to think about all this, right, is you have some kind of your W's live in some manifold endowed with some local metric rho, which is the Hessian of psi, okay? And you're optimizing on this manifold with the corresponding geometry. Okay? Right. So we say natural gradient descent, the way we thought of it here is just an approximation to mirror descent, where mirror descent is kind of the real thing. Okay? Let's try to understand it also a bit more. So we can also think of what happens when you take the step size to 0. And this, in fact, some of the analysis we'll do is for you to take the step size to 0. So you've already seen, I don't know who introduced it. Somebody even introduced it formally, but I think many of the instructors already looked at the gradient flow. Right? So when you take the step size to 0, instead of gradient descent, this becomes gradient flow. Okay? But it's, again, not gradient flow. It's gradient flow according to this metric. Okay? So this corresponds. So probably we're going to define, right, WT, we'll take such that WK is going to be WT times eta, and take WK times eta, sorry. Right. And then take eta to 0, and we get the gradient flow equation where dW dt is minus, instead of the gradient, the inverse metric tensor times the gradient. Okay, and now over, sorry, this is WT. Okay, and now over here, we also have to ask what happens to the stochasticity. And the thing is that once, if we write it this way, then as eta goes to 0, as the step size goes to 0, the stochasticity actually disappears. Because think of it this way, what happens here, right? So in any time interval, right? So in 1 millisecond, okay, as eta goes to 0, we're going to take more and more and more steps. So in every time interval, the number of steps we take goes to infinity. And so the number of different samples we'll see in any time interval goes to infinity, and the stochasticity goes away. What we see is just the expectation with respect to the population. Okay? And so this is, and so here, instead of the stochastic gradient, we can actually write, oops, WT. We can write the population gradient. Okay? And so this is something that's, I don't remember if any of the, if it came up in the other, I don't remember if it came up in any of the other lectures, but the fact that when we take this continuous time approximation, the stochasticity goes away is, depending how you think of it, maybe it's very convenient because there's no stochasticity, or bothersome because if you want to understand the stochasticity, then you can't understand the stochasticity, at least this way. And maybe, I'm not sure, tomorrow we'll talk about how to still preserve stochasticity even in continuous time. You have to do one of several tricks to do that. Okay. Okay, so anyway, we get, so what we see is that when step size goes to 0, then either gradient mirror descent or natural gradient descent, it doesn't matter which starting point you start for, because as I said, they're both, mirror descent and natural gradient descent become the same as the step size goes to 0, and both of them converge to this Riemannian gradient flow on the population. Okay, so gradient flow with respect to some, to this metric tensor. Okay, that's clear? Yes?
Here you have the full function, the f, right?
Right.
And there you have the
stochastic. Right. So as I said, so what happens? Right. So the reason so imagine what happens. So we have some. You take a bunch of steps, right? So this is how the discrete would look like. Okay. This is at least for natural gradient descent. Okay. And now you're taking the step size to be smaller and smaller. So what's going to happen when you take so let's first of all think if you move without stochasticity. So what's going to happen now is you're taking smaller and smaller steps, and this kind of becomes continuous. But the other thing that happens is all these steps are actually stochastic. So maybe they're going kind of each one in a slightly different direction. Once you take smaller and smaller steps, and if I just look at what happens along this arc, I'm going to take many, many more steps. Okay, and so in every, in this time interval over here, the number of steps is going to go to infinity, and so the number of samples is also going to go to infinity, because every step I use a different sample. Okay, and once the number of samples goes to infinity and I average over them, it's the same as just looking at the population. Okay, you get it? So think of it this way: what's the variance in the unit interval? Okay, so the variance in unit interval will. If I look at the variance inside the unit interval, in every unit interval I make 1 over eta steps. Okay? And so the variance will be an average of 1 over eta different samples. And so the variance inside the unit interval will scale as square root of 1 over eta. Okay? The variance the standard deviation would scale as square root of 1 over eta. The variance will actually scale as, I confuse myself now. I take 1 over eta, I'm averaging over 1 over, in any unit interval, I'm averaging, if I take steps as eta, I'm averaging over 1 over eta different stochasticities, okay, different samples. And so the variance of wt plus 1, or let's even say, so let's look at the variance of wt plus delta t minus wt. Okay, it's a crude calculation. Okay, so over here I'm going to have delta t over eta steps. Okay, because with the step size, when there's a function of the step size. Okay, and so this is going to be an average of delta t over eta different samples, and the variance is going to scale as eta divided by delta t. Okay? And so for any delta t, no matter how small, as the step size goes to 0, this variance goes to 0. Okay? And I just get the expectation deterministically. Okay? Is this clear? Questions? Okay. So, right. Right. So the limit of so I have this stochastic, discrete stochastic process, but its limit is actually deterministic. Okay. Okay. This is actually another way to think about what we're doing with stochastic gradient descent. Right. It would be great if we could actually directly optimize the population, right? That's what we want. And in some sense, we see that this is another justification. We're doing something that makes sense, right? As the step size becomes smaller and smaller, we're taking more and more steps. We are actually approaching optimizing the population, which is really what we wanted. Okay, so there's another way to think about natural gradient descent and mirror descent is if it's more natural, so we derive them by starting with a potential function. But another way to think about it is let's start with this Riemannian gradient flow continuous time dynamics. Right. So again, I said this is pretty natural dynamics where I endow my space with some local geometry and I take steps based on that local, or I go based on that local geometry. So natural gradient descent would correspond to a forward Euler discretization of this dynamics. Okay, so we can write it, right? So I'm going to write this, the way I'm going to write this forward Euler discretization is we're going to discretize the right-hand side of this differential equation. Okay, so negative W T eta, where by here I mean t discretized to eta. So formally eta times the floor, the integer part of t divided by eta. Right? So this is just, if eta is 0.01, this is just rounded to 3 digits or whatever. Inverse times the gradient of f w t eta. And now so this is the forward Euler discretization. If I also want to think of it as stochastic version, then I can say that maybe for each step of Euler, I'm going to use a different sample, and that's where I change this to the stochastic counterpart, where also this stochasticity is discretized. Right. So what's going on here? Again, this is a differential equation where this right-hand side is piecewise constant. Right, so I change I take some direction, right, which is given by this right-hand side, and then I stick with it for eta time. Okay, and then I take a different direction and I stick with it with eta time. Okay, so this is just another way of writing the forward Euler discretization. What I guess is exactly the solution exactly gives me this sequence of iterates, right? Because I'm going to start somewhere, pick a direction which is a natural gradient descent direction. The right-hand side of this equation is fixed, so I just go in a straight line in that direction, take another step, and so forth, right? Okay, so this is natural gradient descent, which is maybe the natural discretization. And mirror descent is in some sense a slightly stronger discretization, where what I'm going to do is I'm still going to discretize the gradient, right? Because the gradient I kind of have to discretize because I want to access my function only a small number of times. I only also have a bounded number of samples, but I'm not going to discretize the geometry. Okay? So I have this partial discretization of the right-hand side. Okay? So the way this looks now is in the primal space, instead of this trajectory being piecewise linear, the way it's going to look like is we're going to pick some direction. Okay? And now, instead of taking a straight line in that direction, I'm going to follow that direction according to my local geometry. So it's actually going to look curved. Okay? And then I'm going to do that for time eta. And then I'm going to pick another direction, just like I did here. Okay? Maybe this one. But again, instead of following it in a straight line in this space, I'm going to follow it in a line corresponding to my local geometry. Okay? So it's going to get a trajectory that's kind of piecewise continuous but curved. Piecewise smooth but curved. Okay? And this discretization is exactly equivalent to natural gradient descent. Okay? So I'm actually, for the sake of time, not gonna prove it, but it's pretty easy to prove. And actually, I'm not going to prove it, but I will say I'm going to prove it because I think it's been insightful. So what happens is that the way we can write directly what the solution is going to look like. So the way the solution to this discretization is going to look like, it's not going to be piecewise linear in the primal space, but it will be piecewise linear in the dual space. So we're going to build the solution this way. So we're going to, this is my differential equation, and now I'm going to give you state a solution, and then what I'm not going to do, but you can easily do it as an exercise, is prove that this is in fact the solution to the differential equation. So the way the solution is going to be defined, actually let's write it this way and then change back. I'm going to define WT. So let's call this W K eta plus delta T. Okay, so for what I need to tell you is just what happens between these points, right? So for any delta T between 0 and eta, I'm going to tell you how to move from one point here to the next. And the way we're going to move is we're just going to take the inverse link function of where we were at iteration k, okay, which corresponds to time k times eta. Okay, so this is just wk from my discrete version, plus a linear interpolation of the direction we're going to move it, okay, which is gradient of f at w k eta z k. Okay? So this is my definition, the way I define w, but maybe the better way to think about it is we'll apply the link function to both sides. So let's look at, instead of looking at the inverse link function on the right, we'll look at how this w is in the primal space. Let's look at how its image in the dual space behaves. Okay? So in the dual space, what I'm doing is exactly this linear interpolation. I'm exactly moving from, so this whole happens in the primal space, I'm curved, but this is because in the dual space, I take the image of wk in the dual space. In the dual space, I actually move in a straight line. Okay? And then I map back, all these points map back to the primal space, and that's how I get if this map is a nonlinear map, I'd get a curved trajectory here. Okay? So again, you can think of it in terms of this partial discretization, or another way to think about it is that natural gradient descent is piecewise linear in the primal space, whereas mirror descent is piecewise linear in the dual space. Okay, so these are two different discretizations that we have. Okay, so now one other thing we can see here is that we could have also started, I could have started with this as our starting point, as our remaining gradient flow at the starting point, but then why would I put here the Hessian of the potential function? I'd probably just put here, let's put it in red. I'll probably just put here something like some Riemannian the inverse of some metric tensor. Okay? And right? So even if I start from this starting point of just defining, looking at a, so for any metric tensor, okay, for any, this is a valid flow. It's called, again, the Riemannian gradient flow. And they could have started here and then discretize it in both ways I had here, but the way I had before, where the metric tensor is also discretized, or this mirror descent-like discretization, where the metric tensor is not discretized. They only discretize the gradient. So why did I bother? I mean, maybe this would have been much simpler. Why did I bother you with all this potential function business? And the thing is that the potential function really provides us the link between the local geometry and the global complexity measure, or you think of as potential that we're actually trying to, that's actually implicitly being minimized. Now, a question that we're going to get back to probably next lecture, tomorrow I think, is what happens if I'm optimizing with respect to some local geometry, but this local geometry is not a Hessian map, right? So let's think of the question in reverse. Instead of starting with a potential function, you just started with some manifold, and your manifold is endowed with some metric tensor rho, and then you ask me, okay, what is the actual complexity measure here? So I could try to write rho as a Hessian for some potential, okay? So, oops, there's no t here, right? So this is just a function of the point in my space. So, if I could do this, I'm in good shape. But the thing is that most metric tensors, so what's a metric tensor? It's just a mapping from my space. I'm just going to call it RD for simplicity, although again, you can think of it as a general vector space, even infinite dimensional, a mapping from RD to positive definite matrices, D by D positive, symmetric positive definite matrices. Right? So the only requirement from a local metric is it's some positive definite metric, and maybe I want this to be smooth also, so I have a smooth manifold. Okay? Not any function of this form is a Hessian map. In fact, the vast majority of functions in some sense are not, right? It's very special to actually be a Hessian for some function. Okay, you need the specific condition for this is you need some kind of, in order to be a Hessian map, so in order for this partial differential equation to actually have a solution, what you need is some kind of symmetry. So in particular, you need that D rho ij dwk is equal to d rho ik dwj. Okay, so think of it, if rho was in fact a Hessian, then if I take the ij position of the Hessian is just a partial derivative with respect to coordinates I and j, and then I take a partial derivative with respect to k, then I just get a third order derivative with respect to I, j, and k, and I get the same thing if I change j and k. If I first take the with respect to I and k, and then take it with respect to k. Okay? And so I need, so clearly this is necessary in order to be a Hessian map. It turns out to be essentially sufficient as well. Okay? But this condition doesn't hold in general. Most metric tensors are not Hessian maps. So even a very benign metric tensor, so if you think of, for example, I can look at, define my metric tensor as the identity plus the outer product of W with itself. Okay? Okay? So this is a metric tensor that arises naturally from a manifold. If I just look at if W is in RD, and I look at the manifold that I get by looking at at W in the squared norm of W. So this is, think of the set of all points of this form, W for any vector in RD, W and then the norm of W is a vector in RD plus 1. So in the board here, if you think of W as in R1, then this is this manifold, W comma, in this case, just half W squared. Okay? And now I can look at the geometry on this manifold induced by the standard Euclidean geometry in RD plus 1. It comes out, you can calculate, it turns out to be this, this is the local geometry on the manifold. In this very benign metric tensor, this very benign local geometry actually is not a Hessian map. You can just easily calculate the partial derivatives and verify that this symmetry doesn't hold. Okay? And so if I started really from some metric tensor, being a Hessian map is super special. Okay? And that super special thing really allows us to identify what is the actual kind of complexity measure that's underlying this geometry. Okay? And this is sort of one of the reasons that we went through all this trouble of talking about mirror descent and relating this to psi and the strongly convex psi, being strongly convex with respect to some norm and so forth. Okay. Right. Okay. So let's go back now to mirror descent and think about some examples, look at some examples of mirror descent and how do the dynamics actually look like? Right now that we understand that mirror descent corresponds to some discretization of this gradient flow, remaining gradient flow dynamics. So in order to do that, let's remind ourselves first. Let me erase. Can I erase this half of the board? Okay. 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 Let's remind ourselves how does the choice of how do we want to choose the geometry? So we said that what we can ensure about mirror descent is that, let's say, in expectation over the samples, after running mirror descent for k iteration and also formally have to take the average iterate, then I can ensure that I can compete with, I can ensure suboptimality with respect to any W star, and we'll get back to this maybe in a second, that scales as with the value of the potential function of W star times the supremum of the norm of the gradients of the function. As you recall, we said that the way to think about this is really the data, because for a learning problem, this would correspond to phi of x, or phi of x times some scalar derivative of the loss function, okay, over m. Okay? And this is as long as psi is strongly convex, one strongly convex with respect to our chosen norm. Okay, okay, so so two comments about this. One is I wrote it now a bit differently than I did before, because what is W star here? I actually am not, we're looking at this optimization problem before. We constrained ourselves to W in some space W, in some set constraint set W, and W star was the optimum inside W. I actually don't want to do that now, because the way I want to think about it now is the way we optimize many of these things. We don't think of training a neural network. I don't impose a constraint on the norm of my weight space beforehand. Right? I optimize over all possible weights. Okay? And rather, what we hope is this optimization. That's kind of the story we said in the first lecture. We hope that this optimization is still gonna generalize well with respect to some norm, okay, or some potential function, some complexity measure. And this is exactly what's going on here. What happens is that even if I don't impose, when I run mirror descent, even if I don't impose any constraint, I get that I can compete with any W star, but how well I compete with it depends on how complex it is. Okay? So if I want to compete with some W star that's pretty non-complex, right? That's where psi complex with respect to psi, of course, or psi of W star is small, then I only need a small number of samples or a small number of discretization steps. Okay? If I want to compete with W star that's much, much more complex, then this term would be much larger, or alternatively, I need many more, I'm instinctively writing M here. this should be k, number of steps I take, which is also number of samples. I'm going to take many more samples or many more steps. Okay. So this holds for any W star where I have to choose the step size in a way, and I didn't tell you what the step size I need to use here. I have to choose the step size in a way that corresponds to how complex is W star. Okay. Does this make sense?
So this
Yeah.
is the convergence rate of that.
This is, yeah, sorry, go
Which
ahead.
algorithm?
Mirror descent.
Mirror descent.
Yes. So this is a convergence rate that we had last time for mirror descent. So this ensures that after k iterations of mirror descent, okay, and again, it's formally I put a bar here. I'm looking, instead of looking at the last iterate, I'm going to average the iterates. Okay. So after k iterations of mirror descent with a particularly chosen step size, okay, I can ensure that I get to a point that's at least as good in terms of the population objective as W star plus this term. Okay? Okay? And so now we want to choose you said that like we want to choose the yes.
So when the metric tensor does not correspond to the Hessian, does that imply that there is no global complexity measure?
That's a good question. So that's so the short answer, well, it's some combination of no and I don't know. So, or at least I don't know how to characterize it. Okay, and so that's indeed something. We'll get back to that probably in about 15 minutes. Okay, so that's something that at least the way we wrote it here, no, right? Because we can't, you know, this doesn't make any sense. What I wrote here, like this expression, doesn't make any sense if the metric tensor is not a Hessian map. Okay. Okay, but we'll get to something that makes a bit more sense, and then I'll pose the question of can we generalize this also to cases where the row is not a Hessian map. Okay. Okay. So again, we said last time that we kind of when we ask how we want to optimize with respect to the geometry that corresponds to psi, that corresponds to our thinking of what types of W stars we want to compete with. We want to make sure that the W stars that we think are likely are not complex under this measure. And also we have to choose both psi and the norm W and the norm, and that the data has small norm under the dual norm. Okay? And so the examples, let's repeat 3 of the examples we gave. So example number 1, which is the simplest example, is just the Euclidean potential, which is strongly convex with respect to the Euclidean norm. Okay, and in this case, so what I'm going to look at is how does k scale? So the enumerator for this inside the square root, right? Because that's would tell me how many steps I need to take in order to get some constant to compete with f of w star up to some constant error. And this scales is just with the Euclidean norm of w star times the Euclidean norm of the data. So I'm going to start writing phi of x here. Again, thinking of the gradient of f is corresponding to phi of x for the case of supervised learning. Okay? And the dynamics in this case, so in this case the metric tensor is just the identity, right? It's just the gradient, the Hessian of the Euclidean norm, and so the dynamics are just the standard gradient descent dynamics. Okay. The second example is when I take a potential to be a quadratic potential, but with respect to some other positive definite matrix Q. Okay? So again, this corresponds to I think that some directions are globally more kind of cheaper than others, right? So there's some directions that I don't pay for going in that direction, right? In other directions, those are directions where Q is going to be very, very small, is directions where I think, oh, that's not very complicated to go in that direction. In other directions where I think, oh, it's very complicated to go in those directions, there'll be directions where Q is small. Okay? And this is strongly convex with respect to the corresponding quadratic norm. Okay. And as we talked about last time, here the sample complexity or number of steps comes out to be the proportional to this norm applied to W, and the inverse quadratic applied to the data. Okay. So again, if there's a direction you think it's not very complex to go in that direction, you better not have a lot of data variability in that direction. Right? Because if you're allowing myself to cheaply go in some direction, I'm going to pay dearly. That means that Q is small in that direction. Then Q inverse is large in that direction. I'm going to pay a lot for data variability in that direction. Okay? And the dynamics here correspond to preconditioned gradient descent. Okay? So here we have a global metric tensor. The metric tensor is the same everywhere. And so in all directions, no matter where we are, this Q doesn't depend on W. We always prefer going in the same directions or prefer not going in the same directions. Okay? And the final example, which is probably the most interesting, is the entropic potential. Okay. And the main reason to use this potential is that it's strongly convex. It's one strongly convex with respect to the L1 norm. Okay. And that's very good because we said last time that we're going to measure the data in terms of the dual of the L1 norm. And where we really benefit from here is that the dual of the L1 norm is the L infinity norm, and we only pay for the maximum coordinate in the data, but not for the number of coordinates. Okay? In particular, we mentioned last time that here we get that the sample complexity corresponds to psi of W star, which can be bounded by the L1 norm squared of W star times log dimension. So we have to pay something in the dimension, but we only pay logarithmically in the dimension, and that comes in psi times the L infinity norm of the data. Okay. And how would the dynamics look like here? Okay, I'll leave it maybe for you as an exercise. All we need to do is take this potential and then calculate its Hessian. And when I calculate, write it here. So if I calculate the Hessian, first of all, this potential decomposes over the components, so the Hessian is going to be diagonal, and it's going to be just with 1 over W on the diagonal. Okay, and so if I look at at my dynamics, what happens is I multiply each coordinate by the inverse Hessian. So I multiply each coordinate by the corresponding value of the coordinate. So this is going to be minus diag W times the gradient. Or maybe it's better to write it, the dynamics for each coordinate. So if I look at coordinate I of W, so dW I dt is going to be, instead of just so I'm going to take so for standard gradient descent, or gradient flow, the dW I dt is just the partial, the derivative, the df dwi, okay, just the ith coordinate of the gradient. But here I'm going to multiply it by wi. Okay, so large coordinates I'm going to allow themselves to get larger, whereas small coordinates, even if the gradient is large, is going to be much more expensive for them to be larger. Okay, so again, you can think of it in terms of what is the local geometry here. The local geometry here is not constant like it is here. It's not that there are fixed directions I like to go there or not, but if I already got somewhere and some of the coordinates are large, I'm going to say, okay, those coordinates they already exist. They're fine. I don't mind. It's cheap for me to go in that direction. Even if I have some small gradient there, I'm going to be happy going in that direction. Whereas if I have some coordinates that are very close to 0, that are near 0, that I haven't used yet, it's going to be very expensive for me to start using them. Okay, even if I do have a large gradient in that direction, I'm actually going to barely go there. Okay. So again, hopefully this gives you some intuition for what I mean here by the geometry of optimization. Okay? And then you can at least intuitively think of why this geometry of optimization roughly corresponds to L1, right? So in L1 we want some kind of sparsity, and it makes sense. We can actually, using this way we can actually prove it, but at least intuitively it makes sense that these type of dynamics, right, would get you something like sparsity, right? Because they like using coordinates that are already there, but don't like adding new coordinates. Okay, so this is kind of a dynamics that makes sense for sparsity. Okay, good. So before we move on from the convex case to yes.
Is there 1 over D in the
Over here, over here, over here, over here. This is 1 over D. Yes. So this doesn't. Okay. So the reason there's a 1 over D here. So this just adds a constant here, right? But it's not going to actually affect neither the grade. It's not going to affect the Hessian, so it's not going to affect the dynamics. But I do want my potential function to be non-negative because this, if you recall from last time, this complexity is only correct if the potential is non-negative, right? So the potential, right? Since we only use here gradients and Hessians of the potential, if I add a constant to potential, it doesn't change anything. Right? But for this to make sense, the potential has to be non-negative. Okay. Good. Okay. So before I move on, I just want to briefly mention one thing. So what do I want to erase here? Let me leave this part and erase this. Okay. So the guarantee. The guarantee we wrote here is valid for Lipschitz function. So what we're bounding is bounding the first derivative of the objective. We can also ask what happens if instead we assume our objective function f is smooth. Okay. Again, when we talk about smoothness, we're going to have to talk about smoothness with respect to a norm. Okay. So, oops. Okay, so so I can assume that our population objective is smooth. So what does it mean to be smooth? I'm going to say that f is smooth with respect to a norm. So smooth with respect to the standard Euclidean norm just means that you can think of it as the Hessian being bounded. But if I look at that, what is the Hessian being bounded? I take some spectral norm. If the Hessian is a matrix, I really don't want to talk about it this way, right here, because I want the norm to be explicit. I want to explicitly talk about how things change. Right? So we can also think of smoothness this way. So say that fw prime is bounded by fw plus the gradient of f of w times w prime minus w. Okay, so this is w, and we have f of w, right? And now I'm looking at a linear approximation about w. Since the function is convex, then f of w prime, this is w prime, is always going to be above this linear approximation. And when we say it's smooth, we want to say that it doesn't deviate too much from this linear approximation, right? So it doesn't have too much curvature. Okay? So I'm going to bound this by our smoothness constant h times the norm of w prime minus w squared. Okay? So this is our definition of the function f, the convex function f, being smooth with respect to a norm. Okay? And so this is smoothness h, and again you can think of h as the Euclidean, the equivalent in this norm to the norm of the Hessian. Okay? So for a smooth function, we can get a better a better convergence rate. It's actually, okay. Which depends on, instead of 1 over squared of k, just 1 over k. Okay? So this is if there's no stochasticity, and we also have to pay for the stochasticity separately. And okay, where sigma here is not exactly the variance of the data, because the variance, again, the way I think of at least usually measuring the variance of a vector is in terms of the Euclidean norm, we're going to again have to measure it with respect to the norm we chose. So sigma squared here should be a bound on the expected square norm of the deviations of the stochastic gradients from the population gradient. Oops. But everything is measured under our norm of choice. Okay, so, whoops, this is k. Okay. So what do we see here? Well, first of all, this is it's similar to gradient descent. For a smooth function, you get a 1 over k instead of 1 over squared of k, right? The other thing we see here is now, if we said before that we kind of get the optimization rates and the statistical rates are the same, now we get here a clear separation to an optimization term that doesn't depend all on the stochasticity and is just due to the discretization, in a stochastic term that's just because we're taking stochastic estimates of the function rather than deterministic estimates. Okay? So this already starts allowing us to separate between the notion of number of samples and how much I discretize. So in discretizations we wrote before, the way I prefer thinking about it, we have our continuous trajectory, and the way we discretized it before, we discretized it in two ways. Both, we took this to be piecewise linear, maybe in the dual, okay, but we discretized in terms of the gradient, did a piecewise linear discretization, but also each part of it, we used a different sample, and by that we had more, we used more samples. In both of these discretization, we took to be the same. The right thing to do turned out to be to take the same number of steps as points. What we see here is that since the optimization is in some sense much smaller, much easier, it scales as 1 over k than the statistical part, it makes sense to actually take many more samples than discretization steps. Okay? So how can we do, we have our stochastic objective, how can we take more samples than discretization steps? What type of method would make us take more, take less gradient steps than samples? A batch, right? So what we did is exactly do a mini batch, right? So if I calculate my stochastic gradient estimates instead of just as the gradient of f at a single z, I calculate them as an average over b random samples zi, my effective variance scales as 1 over b, okay? And I get a factor of b here, but this doesn't change, right? I mean, it doesn't matter how large the batch size is. This doesn't depend on the variance. This is just because of the discretization. And now this tells me exactly kind of how big a batch size am I allowed to take, right? I can, if b is equal to 1, if there's no batch, then this is going to be probably the dominant term because it scales as 1 over k. And then can allow myself to increase my batch size until this stochastic term becomes of the same order of magnitude as the optimization term. If I increase my batch size beyond that, that means that I'm using my stochastic term becomes smaller than my optimization term, and that means that I'm taking, in some sense, I'm needlessly using very, very large, very precise gradient estimates for each discretization step, but I'm not benefiting from that because what's holding me back is my discretization. Right, so the right batch size to take is that makes both of these terms about the same. Okay? And the other thing we see here is that for smooth convex optimization, somehow inherently optimization is easier than the statistic aspect. Okay, so what's holding me back is really the number of samples. And so it never makes sense to take more steps than number of samples. Right? Maybe I want to take less steps than number of samples, but not more. Right? Unless maybe my variance is extremely small. Okay? And because of that, sort of even maybe I want to take mini batches, but I still want to do like a one-pass method. It never makes sense to reuse samples. Right? Because really I want to, my limiting factor is the number of samples, not the optimization. And so I really just want to use all my samples. If I did that, then probably I already optimized. Okay? In the non-convex case, that's definitely something that would be substantially different. In the non-convex case, the optimization complexity might be actually the more complicated factor compared to the statistical. And so it might make sense to actually reuse samples. Okay, that's one comment about that. Also, I should say that I actually don't need to calculate this variance everywhere. It's enough for me to calculate the variance just at the optimum. Okay. Oops, this is W. Okay. It's enough for me just to calculate the variance at the optimum. Again, not exactly variance, but this stochasticity in the optimum. And this is important because if the problem is realizable, okay, then at the optimum, the loss for any z is 0. So this would be, the gradient, if the problem is realizable, right, and f is not negative, then at the optimum, W star is the best for any point z. And so these gradients are all 0, right? Okay. And so I don't have any variance at all, actually. And this is a real thing. I can actually bound this instead of, in terms of the variance, I should say this is for non-negative objectives as just the optimization term plus square root of h times the value at the optimum times size. Okay, let's forget about erase the mini batch now. Okay, and so if the problem is, if my target objective value, if the problem is not simple, I cannot get 0 error, right, on the population. F of W star is large, then I have to pay this 1 over square root of k. But as the problem becomes more realizable, becomes easier, I can actually get 0 error. F of W star goes to 0. This second term disappears, and I just have the 1 over k term. Okay. The last thing I want to say about this, which relates to, I think, your question, okay? So there's something bothersome about this, this analysis, because this analysis relies not only on the choice of potential function, but also on the choice of norm, right? So we didn't write the norm explicitly. Well, here the norm appears explicitly. In H and sigma, both also depend on the norm, right? The H is smoothness with respect to this norm, and this is the variance with respect to the norm, to the dual norm. Okay, but the norm actually doesn't appear in the algorithm, right? The algorithm only depends on the potential function. Okay, but somehow for the analysis, it's not enough for me to choose a potential function. I also have to choose a norm. Okay? So there's a recent analysis of mirror descent that alleviates much of this and replaces this condition of so the standard analysis have to choose a norm, make sure my potential is strongly convex with respect to that norm, and then measure smoothness with respect to that norm. Instead, I can just rely on relative smoothness. Okay. So I'm going to say that my objective function f is smooth relative to the potential phi if the Hessian of f is dominated by the Hessian of psi up to some smoothness constant, the smoothness constant h. Okay, so okay, this, you know what I mean by matrices are dominated? Where should I find? So this notation means that the differences between the matrices is positive definite. That the right-hand side minus the left-hand side is positive definite, positive semi-definite. Okay, so if my potential function was the standard Euclidean, the squared Euclidean norm, then this Hessian is just identity. And what I get here is the standard notion of smoothness, that the Hessian is dominated by H. All the eigenvalues of the Hessian are bounded by H. And instead, what we're saying here is that the bound on the Hessian of F can be non-uniform. At every point in the space, it's given by the Hessian of psi, which is our metric tensor. So I have to be in places where my in places in space and directions in which psi is very curved, then f is also, the objective function is also allowed to have high second derivative in those directions. Okay? So it turns out that I can replace, in all the analysis, I can replace smoothness with respect to a norm to relative smoothness. Okay? And in particular, here I still have this notion of norm. Something that I'm actually not sure is correct or not. I tried to figure it out for this lecture, and I couldn't easily, okay? Because it wasn't the different kind of communities looked at this. I don't know. So this guarantee is definitely valid based on relative smoothness. This guarantee is actually much more attractive because it avoids, here we still have a norm because the norm appears inside sigma. But in this guarantee, there's no norm at all. Okay? And if one of you wants to look at that, I'm actually I think that it's possible to easily get this guarantee as well based on the relative smoothness analysis, though I'm not entirely sure. This will be very satisfying because now we have a guarantee that doesn't depend on the norm. And so that already gets us a step forward towards something that, if I now have a general metric tensor, relative smoothness I can define for any metric tensor. Okay? Just formally, I can write down being smooth relative to a metric tensor. Okay? I don't care that whether this is a Hessian map or not. Okay? And this could be a starting point for analyzing gradient flow with respect to a general metric tensor that's not a Hessian map. Okay, but again, I have no idea how to do it. Okay, right.
This last inequality was for the regular.
So this is correct with regular smoothness
When f is positive.
when f is positive. Okay, and I think it's correct also with relative smoothness, but I was not able to verify it. So this work on relative smoothness is relatively recent, from the past 3-4 years ago. 3-4 years. So, and the people working it were not looking at these type of guarantees. Okay. Last thing I want to say is that you can also beyond talking about. So we talked about mirror descent and related it to. Well, I don't have it anymore. Okay, to remaining gradient flow. You can also think more generally about steepest descent methods that are not even with respect to a particular metric tensor. So formally, I just want to mention them. Maybe I'll do it. Let's erase this. Okay. So I can define steepest descent kind of similar to what I did here, but forgetting the requirement that this is a Bregman divergence or corresponds to any potential or even a metric tensor or a metric or anything. Just define it as minimizing the stochastic linear approximation plus some any kind of, I don't want to call it even distance measure, I don't know, discrepancy measure between W and W prime. In particular, maybe times step size. Okay. Oops. Okay. In particular, I can take this to be a norm distance. So, and the main relevant choice here is the L1 norm. Okay? So we might think that doing this would correspond, so if, using the L1 norm as a proximity measure might correspond somehow to using L1 geometry. And we'll see actually that it maybe sort of does, but not exactly. It's also, the algorithm here is very natural, so steepest descent with respect to the L1 norm corresponds to just coordinate descent. Because each time I might, I might as well just take the coordinate with the highest partial derivative and change it. That would be cheapest in terms of the L1 norm. Okay? So this would correspond to steepest descent. You can also think of, sorry, this would correspond to coordinate descent. And you can also think about steepest descent with respect to L infinity norm, and that would be the opposite of coordinate descent. That would be on each taking a step that corresponds just to the sign of the gradient. So for each coordinate, if you take the amount you go is the same, you just go in the direction corresponding to the sign of the gradient. It doesn't. It's not something that makes much sense, but just if you want to think about it. But this is the main example of steepest descent. And I'm just mentioning it because we'll get back to this later. And again, this is another maybe. There's not much theory here, but heuristic way of thinking about using some specific geometry and optimization. Again, the main rationale here in all of these is you want to take steps that are small with respect to some notion of locally what does it mean to be close. Okay, excellent. Okay, so let's just summarize where we are. So far we talked about the convex setting. And we related optimization and generalization. So these guarantees are all generalization guarantees. They give you a guarantee on the population suboptimality, a learning guarantee. This is what we wanted. And this comes out only from the optimization, right? So we didn't, in order to get this, we competed with some W star, and we didn't put any constraint on our optimization. We got this. We got the fact that we can compete with W star only by virtue of how, what was the dynamics of optimization, and we saw that, we understood the connection. Hopefully, we understood the connection between the geometry in which we're searching the space, and the corresponding complexity that it corresponds to, like that we can find solutions that are small under this complexity. Okay? But all this was, well, first of all, it was only in the convex case. And second is, this isn't quite what we're seeing in what we saw in the examples we saw in the first lecture for deep learning, because in these methods, we're not actually driving the training error to zero. Right? So in all this, I'm not actually getting a zero training error solution here, and the generalization seems to really rely on the fact that we're also using stochasticity, right? So we have stochastic gradient descent. We're doing kind of one pass stochastic gradient descent, and we're maybe kind of getting regularization from that. That's different from what we saw in the examples I showed you, where we're training, and maybe even with full batch gradient descent or multi-pass stochastic gradient descent, driving the training error to zero and still getting generalization. Okay. And just to kind of maybe draw a figure that maybe would help explain what's going on here. So we start optimizing from W naught, which might be the origin. Okay? And we have this W star that we want to compete with. Okay? Maybe it's the best we can do, maybe even. Okay? Then we have two approaches, and we said that we can, on one hand, we can take what we'll write this here, okay? We can take an explicit regularization approach, which we also analyzed last time, and define W lambda as the minimizer of our training error based on K samples, plus an explicit regularizer. Or we can take W bar K, which corresponds to K iterations of mirror descent with the same potential function. And both of them would have the same generalization properties, but they would actually be very different predictors. So in some sense, if I look at W lambda with the optimally chosen lambda, we know that it's going to be, at least for the Lipschitz case, it's going to be a distance roughly 1 over square root of k from the optimum. Okay, in terms of this, not really distance, but suboptimality of square root 1 over k. If I use mirror descent, okay, then I'm also going to get to something that has the same suboptimality, in some sense, the same amount close to W star. Okay? But it's actually not going to be the same as using explicit regularization. It's not that running mirror descent gives me the same predictor that I've gotten with explicit regularization. Okay? I get to a different point here, W bar, okay? And this W bar is also, the guarantee I can get for it the same, but it's just in the same neighborhood. In fact, the distance between W bar and W lambda is also 1 over square root of k. And we know that because we know that we can actually optimize also the training. Instead of optimizing the population error, we talked about how I can also view stochastic gradient descent as optimizing the training objective. And if I only do one pass, then up to issues of sampling with replacement and without replacement, they're not really significant. Maybe they're off by at most a log factor. This is the same as actually optimizing the training objective. So in my suboptimality with respect to the training objective would be just the same, square root of 1 over k. So we're saying it's not that we can characterize the point we're getting at as explicit regularization and then use the generalization guarantees we have for the explicit regularization, but actually we're getting to a different point with the same generalization properties. Okay? And just to see that we understand what's going on here, so we said that this is one pass over the data, and up to here, there's not really any difference between optimizing the training objective or the population objective. Okay? It behaves the same as both. Once I do more than one, once I do multiple passes over the data, this is when k equals m being the number of examples and k being the number of steps, then it's important whether I'm optimizing a population objective, in which case I'm going to have more samples. Okay? And if I do that, then I'm actually going to get closer and closer to the population, or whether I'm optimizing the training objective. Right? If I'm optimizing the training objective, then I'm actually just resampling points. And if I do that, then where I'm going to get to is not to this W lambda, because the objective I'm actually minimizing here, if I view it as if I'm using sample, I'm just minimizing the unregularized training error. If I start doing more and more iterations using the same sample, so multipass SGD, what I'm going to converge to is actually the unregularized population, unregularized training error minimizer, so just the argmin of the empirical error, of the training error. And in general, that can be very bad. Okay? And the phenomenon that we started with is said, well, actually, maybe minimizing the training error, sometimes maybe it's going to be bad, but sometimes it's not going to be bad. And can we actually understand what is this point, especially in underdetermined problems, which there are many ways of minimizing the training error, can we actually understand what point we're getting here, and does it actually have good generalization properties? Okay? So that's going to be what we're going to do next, except I'm not sure there is much time for next right now. Okay, we have 10 minutes or so, right? Yeah, okay. Let's start doing that just so we feel that we actually started with something, and then we'll finish tomorrow. So our goal is to understand how a particular optimization algorithm under a certain optimization geometry, what kind, where is it going to converge to, in particular for underdetermined problems. And the first problem we're going to start with is actually an example we already briefly mentioned in the first lecture, and we're going to do it a bit more formally now. And this is just gradient descent, which we now understand that gradient descent corresponds to optimizing with respect to Euclidean geometry. And we're going to look at an objective exactly of this form. Okay, so actually I don't need to copy it. So we're going to look at an objective of this form. And you can think of the loss here as a squared loss. Okay, but we don't even need it. It's a squared loss. All we need is the way. So if you think of the loss function, so this is the loss between the predicted label and the correct label. All we need is this loss function is minimized only at the correct label. So it looks, should look something like this. And maybe also just to ensure convergence, we want it to be convex. But it can be the squared loss, it could be the absolute loss. If you want to think of it the squared loss, that's fine. Okay? We're going to analyze gradient descent on the unregularized population objective. Okay, so this is sum over m examples of the loss of w xi yi. Just so I wouldn't have to write lots of phi's, I'm going to drop the phi right now. So in your head, you should always think about this as some feature map maybe, but we're just going to think of linear functions of x itself. And so the gradient descent iterations, when you're given by wk plus 1, is just going to be wk minus some step size times the gradient of this empirical error at wk. Okay? And let's, for simplicity, start at the origin. Okay? And this problem so we're going to get to this is a convex problem. If the loss is convex, we're going to get to a minima. But again, the case we care about is when the problem is underdetermined. When w is an RD and d is much bigger than m. Okay, so there are many global minima. There are many ways to get zero error here. And the question is, where are we going to get? So I think we already mentioned, so it shouldn't be a surprise to you, that the place we're going to get is the minimum Euclidean norm solution. But I want to do that formally because what we're going to do next is modify the proof in order to understand what happens if instead of gradient descent, we use mirror descent. Okay, so to prove this, what we're going to first argue is that all the iterates wk always remain in a linear manifold, which is just given by the span of the data. Okay, the span of, let's denote the matrix x here. So x is in m by d. Okay, the span of x. So just all the vectors of the form x transpose times s. Okay, so this is an m-dimensional linear manifold inside this d-dimensional space. Right? Okay, so why does this happen? I mean, if we look at the gradient descent iterates, we're always just adding gradients multiplied by some scalar to wk, and the way the gradients look like is just the sum over the gradients of each point, and the gradient of each one of these terms is the derivative of the loss, which is just some scalar. I don't care what it is. It corresponds to residual maybe, times the gradient inside here, which is just xi. Okay? So all the gradients are just linear combinations of xi's. Okay? And so each time I just accumulate more and more linear combinations of xi. Another way to think about it, and this is maybe a very simple version of this, is that I have this linear manifold, and you can already guess that it's soon going to become nonlinear. So you have this linear manifold, and my gradients are always tangents to this manifold. So if I started this manifold, I stay inside this manifold. Okay? Okay, so the thing is, this already tells us a lot about what we're going to get, because we have this huge d-dimensional space, but we're actually limited also only to an m-dimensional space inside it. Okay? In which of the m, we still have an m-dimensional space of possible places we might get to, but we also know that at the end we're going to actually find a zero-error solution, because this is an underdetermined problem, and we will converge to a global optimum. And in all of my proofs, all my derivations, I'm going to always assume we get to the global optima. That's not always trivial to actually show. It can be shown, but that we're not going to bother ourselves. We're just going to assume that we actually get to the global optima. And so in the global optima, I also have that xw is equal to y, right? That I have zero loss. Okay? So this gives me m constraints. And now I should be done, right? I know I'm in an m-dimensional space. I don't know which point in that m-dimensional space, but I just gave you m linear constraints. Okay, so now this defines a unique point, but which point? Okay, so what I claim is that the point I get is exactly the minimizer of the. Actually, I want to use a different pen for this. Okay, of this optimization problem, the minimum Euclidean norm subject to xw is equal to y. Okay? Okay, so again, so we have two different optimization problems, and this is going to be something that's going to happen in all these analyses. We have the optimization problem that we're presumably optimizing, which is just minimizing the empirical error. And I have that's the white optimization problem. And what I'm claiming is that I'm implicitly solving this green optimization problem. Okay? So how can I prove to you that I get to an optimum of the green optimization problem? Let's look at the KKT conditions. We know that the optimum of this problem is uniquely characterized by its KKT conditions. Okay? So let's look at the KKT conditions, the Lagrangian here. So actually, maybe I should check. People familiar with the Lagrangians and KKT conditions? Yes? Okay, good. KKT conditions, no? Okay. So, okay. Let me just finish this, and then, because I see many people are. So the KKT conditions are, so if you have an unconstrained problem, its optimum is obtained just when the gradient is equal to 0. And if you have constraints, then instead of looking at the gradient equal to 0, you have to look at the gradient of Lagrangian equal to 0. Okay, for at least, for now, this is good enough. If you have inequality constraints, maybe, which we'll have later, it gets a bit trickier. Okay, so the Lagrangian here, we have to introduce dual variables for these constraints. In the Lagrangian is just the objective plus the dual variable times, I'm actually going to write it as y minus xw minus the constraint. Okay. In the KKT optimality condition is just we have here just stationarity, so I want to set the gradient of the, oops, not x. I keep, okay, sorry, optimization variable is w. We want to take the gradient, set the, find primal and dual pairs so that the gradient of Lagrangian with respect to w is 0. The gradient of Lagrangian is just w plus minus x transpose nu, or in other words, w is equal to x transpose nu. Okay, and primal feasibility, which is just xw is equal to y. Okay, so if we find a point satisfying these two conditions, we know that it's optimal with respect to this problem. And these are exactly the two conditions we have here. Right? So at the optimum, I know that xw equal to y. I have primal feasibility because I got to a global optimum. And also I know that w is equal to x transpose s for some vector s. And this vector s is going to exactly become our the dual variable here. And we know that we got to an optimum point. I'm going to take 10 more minutes. Because I do want to actually tie this back to mirror descent. And then next time we'll start talking about other models. Okay, so this is analysis for gradient descent. Now let's see what happens for mirror. So we already have our first implicit bias analysis. But now let's see what happens for mirror descent. So as you can expect, what we want to say is that if we optimize using mirror descent, we're going to get to instead of a minimum Euclidean norm solution, we're going to get to a solution that's good with respect to our potential function. And that's, of course, exactly what we're going to get, unsurprising. So to show that, we're going to use essentially the same proof. Okay? So we're going to optimize f hat using mirror descent, and recall that the way I'm going to, so if the mirror descent iterates, I'm not going to rewrite them, but the way that actually would be useful for us to think about them, recall that we said that what happens in mirror descent is that we accumulate the gradients, but we accumulate the gradients in the dual space. Okay, so wk plus 1 is equal to the mapping back to the primal space of the accumulation of the gradients. Okay, so let's use that as our starting point. Oops, sorry, we're talking about the white problem. So again, we have our white optimization problem, which is just minimize. Where is it? The same, actually. Minimizing the same. So it's the exact same optimization problem, right? So we didn't change the white optimization problem. We're only changing the optimization algorithm. Our optimization algorithm is now mirror descent with respect to some potential function psi. Okay. And what we can say then is that wk is the inverse link function applied to the initial starting point in the dual space. I'm just copying from here. And then an accumulation of the gradients. I'm sorry. Now, again, all I'm going to use is the same thing we used before, is that all these gradients are spanned by the data. Again, just to think about spaces, so one thing I hope you're going to get from these series of lectures is that the gradients are in a space that's different from the primal space. We have our primal space of W and the dual space of gradients. Okay? Okay? Is it okay? Or okay. And the data, in some sense, also lies in the space of gradients, right? So this is a space of gradients, or the space of data. This lies in the span of the data. Okay? And so, again, instead of looking at wk, okay, so again, we can say that now wk, okay, again lies in the manifold. But this manifold is going to be all the points of the form, this form, plus something spanned by the data. Okay? So this is again a d-dimensional manifold inside an m-dimensional manifold in d-dimensional space, because S here is just m-dimensional. So it's a manifold parameterized by just m parameters. And it's not a flat manifold. It's flat in the dual space, but it's not flat in the primal space. But that's fine. Okay? And to know which point we got to, again, we're going to say that at the end we converge to a global optimum. So we know that xw is equal to y, same as before. So again, we're limiting ourselves to m-dimensional space. We're intersecting that with m-linear constraints. That should uniquely specify the point we get to. And in order to see what point that is, we'll again write a green optimization problem. And we want to write a green optimization problem that's its KKT conditions matches what's going on here. Okay? And our green optimization problem this time would be, give me some more space here. It would be minimizing the KL divergence between W and W prime, again subject to XW equals Y. Okay? So our claim here would be we're going to converge to the point that's closest to where we started under this divergence measure. Okay, so again, let's write down the KKT conditions here. So the Lagrangian in this case, again, would be the objective function plus nu times the constraint. And setting it to 0, I have the stationary condition. We have to take a gradient of this with respect to W. We have the gradient of psi at W, and then this doesn't depend on W, and here I have minus the gradient of W naught, the gradient of psi at W naught, okay, plus the gradient from here, which is X transpose nu. Okay? So the K and D conditions, extracting W from that, solving for W, we get the K and D condition. Okay, sorry, plus primal feasibility. Did I write? Okay. And now, just solving this for W, we get that this stationarity condition is equivalent to W equals psi inverse times psi gradient of psi of W naught plus X transpose nu. And again, this is exactly the two conditions we had here. That xw equals to y, primal feasibility, and being on the manifold ensures that w is in fact of the form inverse link function times link function of w naught plus some combination of x's. I think the way I wrote it here, the dual variables will be minus s. Okay, nu would correspond to minus s. I think I meant to write it maybe otherwise, but I flipped the sign somewhere, which is fine. Okay, okay. So again, so what we showed using the same technique of matching. So in both of these cases, the technique we used, and we'll see more examples of it next time, is that we started from a white optimization problem. We said that the trajectory of this white optimization problem remains inside a low-dimensional manifold. We intersected that with the fact that at the end we get to a global optimum. That defined a unique point that's defined by two sets of constraints. One is being on the manifold, and the other is being globally optimum. And we match those two conditions with the KKT conditions for some implicit green optimization problem. Okay? Should just say that here we wrote it as minimum of the divergence. A particularly relevant choice is if we start at our least complex point, if we take W naught to be the minimizer of the potential function, okay, then if we look at the scale divergence, this term goes away, okay, because the gradient at, if W naught is a minimizer of psi, the gradient of psi W naught is 0. And the scale divergence just amounts to the potential function of W. So if we initialize in some sense in the origin with respect to, you can think of this point as the origin with respect to psi, right? This is the least complex point according to psi, okay? Then this optimization problem just becomes minimizing the potential function of psi subject to xw equals y. Okay? Okay, so we'll end here for today, but we already, what we already saw is how the effort we put into mirror descent already kind of paid off because we can now characterize also in terms of like where we get to, we can characterize, at least in cases where we can actually write our optimization as mirror descent, write the local geometry as mirror descent, we can understand the implicit bias in terms of a potential function. And what we'll see next time is even in cases where we don't start with mirror descent, if we actually don't start by, oh, I have some potential function, I start with some dynamics. So we're going to start with a local geometry with some local metric tensor. We can uncover a potential function that corresponds to it. And once we do that, we're all set. Okay? But even here we see that, you know, for this, for cases we do use mirror descent explicitly, like for example with respect to entropic potential, we know exactly what the implicit bias is going to be. Okay, so that's all for today, and I think I'll see you tomorrow, I think, right? Yeah. Okay, and sorry for messing up your schedule. I think Andrea is not here to. Thanks.